So this is going to continue our discussion on solid structures. And so I'm going to start off with molecular crystals, or what we call covalently bonded molecules. So these are held together by forces, mostly dispersion, but you could also have dipole-dipole and hydrogen bonding in these molecules. So, and of course, hydrogen bonding is going to have the strongest force in those molecules that we're talking about. So realize that molecular crystals, we're talking solid structures, but most covalent molecules are gases and liquids at 25 degrees Celsius. But you can change, again, the temperature and pressure in order to get it into a crystal structure. So that's why, again, we don't really mention them too much because they are pretty weak, not very common to have molecular crystals in inorganic or first-year chemistry student in college. So these molecular crystals are generally going to be soft. They're going to have what we call low melting points, and they're going to be poor conductors. And that's because, again, you just don't have a flow of electrons with these crystals as you do with other things. So those are molecular crystals. Then we go to metallic crystals, okay? So what do you remember about metallic bonds, okay? So remember that we taught you, we call it a sea of electrons, where we would have a cation, and then we would have electrons not dissociated essentially from that atom, where those electrons could flow. And that's where our idea of sea of electrons came from. Well, in AP chemistry, you can't use that term. You need to get a little more sophisticated in your explaining. So in a metallic crystal, we have a metallic bond. That's really what's driving all of this. But this is going to be the definition, or what you're going to have to understand about a metallic bond. It is valence electrons are delocalized over the whole structure. So those electrons don't belong to any one iron nucleus. They belong to the whole structure. So that is why you have those properties that you do with metals. So the key word here is delocalized. So again, get out of the idea of sea of electrons and focus more on delocalizing the electrons. So what do we know about properties of metals? Well, we have, depending upon the metal, they could be soft or hard. So that's why it's not going to be a hard rule to say, okay, metals are always considered hard. They have low and high melting points. You might know that gallium has a very low melting point. You might have seen some videos of people holding out their hand and putting a piece of gallium in their hand, and you can melt it in your own hand. So it has a very low melting points. A lot of metals have high melting points. They are very good conductors, though. Okay, that you will definitely need to know, and that is because, again, since those electrons are completely throughout the whole structure, you can conduct very nicely. And that is why metallic crystals are malleable and ductile, because you can shape them into copper wires, sheets like aluminum foil, because of that structure, So in that same idea, okay, we can also look at something called alloys, okay? And alloys are, by definition, a substance that has at least one metal in the mixture. Usually you have multiple metals in the mixture, and you might know of some alloys like bronze, brass, sterling silver. There's quite a few alloys that you probably know in your everyday life. Well, in terms of their structure, and again, not a big focus on this, there's two different kinds of alloys. One is called a substitutional, where the metals are the same size, meaning they are close to each other. So they substitute with each other in terms of each atom when you mix them together. Interstitial is when you're filling gaps with smaller metals or elements. A good example of this is iron steel, where you could have iron mixed in with something smaller. And so the gaps that iron has in it naturally are filled in with a smaller element or a smaller metal to make it have different properties associated with it. So the last solid that I want to kind of talk about is probably the weirdest of them all, which is what we call a network solid. These are actually covalently bonded molecules, but they have very unique characteristics that are not typical of a covalent molecular crystal structure. They have covalent bonds, but their structure is very different. So what I have in your notes is two pictures. One is a picture of a diamond and one is a picture of graphite. But both of them are carbon, okay, atoms repeated, okay. We know graphite to be pencil lead, okay. And as you could see, the structure of this is that there are layers, okay. There are layers of these atoms linked together in kind of these hexagonal shapes. Because you have those gaps there, this is not a very strong structure. So if you know graphite in your pencil lead, it breaks very easily. But if you organize the carbon atoms into what we call a covalent network solid, the carbon atoms in like a diamond are all interlinked. And so, yes, it is considered still to be a covalent bond, but you have a stronger force. And so that is why network solids have such unique properties, okay? They are considered to be very hard, okay, while molecular covalently bonded molecules are considered to be very soft. Network solids have high melting points, and please note that they are poor conductors. So this again is on page 503, and that's the section in your book that they talk about networks. The only other one I want to mention is silicon dioxide. That's a pretty popular network solid for you to kind of keep in mind. So kind of like with most things in science, we have these compounds that don't quite fit into a normal mode. So we have this category of network solids that explain, while diamond is the network solid, so please make sure you understand this is a network solid. And that's why diamonds are used for drilling purposes and other things, while graphite is considered a covalent molecular compound. Okay, so again, those are kind of wrapping up the solids and what we're talking about in chapter 12.